Now, the velocity versus time graph isn't always linear. That is the case for what we call uniformly accelerated motion, which is the easiest type of motion to deal with. And uniformly accelerated motion is dispensed with here in 3 lines, and we'll get to that. But let's first consider a case that's fairly familiar to you where it's not the case that the motion is uniformly accelerated. For a pendulum, and let me just kind of sketch a short representation of the free body diagram for a pendulum. We have the weight acting down here, and we have the tension in the string acting this way. The vertical component of the tension is equal to the weight. And if we want to then figure out the resultant force, that's going to be pretty much in this direction, and it's going to be equal to the x component of the tension force. The further we pull the object back, the greater this force is compared to this. Okay? And the one thing that's constant is this force. Now, if you work that out, you find that this force is actually quite complicated. It actually has, you can expand it in a polynomial, and you get higher and higher order terms that are less and less significant in their contributions to the force. If you do this at a first approximation, and that first approximation simply corresponds to a small displacement so that there's very little difference between the magnitude of the tension and the vertical component of the tension. The vertical component of the tension always being equal and opposite to the weight. In that case, you can do this with similar triangles, or you can do it with trigonometry, and you can determine that the force here is just a linear function of x. So the force is negative kx. Now, we haven't really covered it, but it should be general knowledge that F equals ma, Newton's second law. The force required to give a mass, the net force required to give a mass and acceleration, given acceleration is equal to the product of the mass and the acceleration. From this, we can write ma equals negative kx. Now I chose to write ma of t equals negative kx of t, where a of t indicates the acceleration is a function of time, and x of t indicates that x is a function of time. And we want to apply this to the pendulum as it's freely swinging, because the closer it swings to equilibrium, the less force there is. The further it swings out from equilibrium, the greater the magnitude of the force. The force is always in the direction opposite the displacement from equilibrium. So very easy to understand where this comes from. For the people in this class who have statics courses and understand this free body diagram quite well, we're going to move this on to dynamics, and most of you are taking the dynamics. I think all of you are taking a dynamics course, so this is going to be helpful to you there. What we want to do is we want to solve this equation to find what this function x of t is. Now, of course, having found the x of t function, we can easily find the a of t function by taking 2 derivatives. Because we know, and we talked about it last time, that the acceleration is the acceleration function is the second derivative of the position function. That's our definition of acceleration. Okay, well, in that case, we're going to go back to writing x, but remember x represents a function x of t. We're going to go back to writing, well, we're not actually going to write a, we're just going to observe that our acceleration function is the second derivative of our position function. And then we can solve this for x double prime. It's equal to negative k over m times x. And we observe that this side is just a linear function. Well, it's just a, let me back up. What I started to say wasn't right. The right-hand side is a constant multiple of our position function. so that our second derivative is a constant multiple of our position function, k and m both being constants, k being the force constant, the constant that you multiply by your position with relative to equilibrium to get the force, m being the unchanging mass of the pendulum. Okay, well, now, let's ask the question. We've again observed that this function has a characteristic that its second derivative is a scalar multiple, a constant multiple of the function itself. What kind of function has a second derivative equal to a constant multiple of itself? We observed that, say, if your function x was t squared or some multiple of t squared, well, its second derivative would then be a constant. And there's no multiple of your function, which would be, let's say, a t squared function, that's equal to a constant. So that can't happen. The function x of t can't be any power function or any polynomial, for the simple reason that when you take two derivatives, you reduce its degree by 2, and a polynomial of degree 2 less than another cannot be equal to constant multiple of that polynomial. Well, then people, after we thought about this for a little bit, somebody suggested, well, sine and cosine functions. That's true. The derivative of the sine is a cosine. The derivative of the cosine is the negative of the sine. Now, we need to take account of the chain rule, but we're going to do that. And then somebody else came up with the suggestion exponential functions, and that's also the case. Okay? Now, actually adding exponential functions doesn't add much because of the Euler identity, e to the I theta cosine theta plus I sine theta, I being the square root of -1, so this being an imaginary and this argument being imaginary. This is easily derived and easily verified, incidentally, from power series. If you write down the power series for cosine theta, the Taylor series, and that's 1 plus x squared minus x squared over 2 plus x to the 4th over 4 factorial, etc. The sign is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. And you can easily do that. You might have to review what a Taylor series is and how you obtain the coefficients, but it's very simple. And then e to the x would be 1 plus x squared over 2 plus x cubed over 3, and so forth. Well, if you plug in the power functions for cosine theta, I sine theta, which you multiply by I, and then for e to the I theta, and expand that, you find that this is equal to this. So that the cosine and the sine function, surprisingly, come directly from the complex exponential function. Exponential function to an imaginary power. This is a very, very powerful idea, as you're going to see in differential equations, and you'll use it again and again as engineers. So without saying too much more about that, just saying that's really, really important. And what we're doing here is really important, and it'll give you a head start when you take a differential equations course in a few months. Now, so let's go back to this now. Okay, so we've established that the second derivative of either a sine or cosine is a negative multiple of itself. For an exponential function of a real variable, that is where we don't put an imaginary up here, the derivative is equal to a positive constant multiple. Okay, assuming that you're, well, your second derivative won't be a negative constant multiple. Okay, whether your exponential function has a positive exponent or a negative exponent, the second derivative is going to give you a positive multiple. So, second derivative of a negative constant multiple of itself, excuse me, that would require a sine or a cosine function. It would not work for an exponential function with a real exponent, but it would work for an exponent with an imaginary, like an e to the it or something like that, because two derivatives e to the it is going to give you I squared e to the it. I squared is -1, so you would have your negative multiple. But we kind of cross that out. Later on, you're going to want to use this. Okay, you're going to want to use this form of the solution. For right now, let's just stick with what we know about first-year calculus, which is that the sine or cosine function can give you a negative multiple of itself when you take its second derivative. Okay, so now let's just assume that and did I ever write down what we're assuming? Yeah, I'm going to pause for a second and write down what I should have. I said it, but I didn't write it down apparently. Well, I wrote it down, but as I was writing it down, I distinctly remembered writing it down because I remember getting down here and referring back to it, which led me to look up here, and right there it is. Okay, so we let x equal a sine of ct. Just going to use c for a constant multiple of t. Then x prime is a times the derivative of the sine of ct. Now I went through the details of calculating the derivative of a sine of ct. Okay, and I didn't go through. Yeah, I could have added more steps, but applying the chain rule, you will remember, and you should review and make sure you really understand the chain rule. But the derivative is going to be, first of all, the derivative of ct. This is like an f of g of x. You take the derivative of your g of x function. So the ct prime, derivative of this inner function, and then times it's the derivative of the cosine of the sine, which is the cosine of the original argument ct. And then the derivative of ct, well, ct is a constant multiple of t. We can factor out the c. It's c times the derivative of t. I probably didn't need to write that down, but I did. And t prime is just 1, so we get just c. And then we put the c out in front. We have ca times the cosine of ct, so that now x double prime is negative c squared a sine of ct. Okay, now we can plug into our original equation, which was x double prime equals negative k over mx. And maybe I should write that out up here. X double prime equals negative k over m times x. And this expression goes in for x double prime, and a sine of ct goes in for x. Well, we get an equation. We look at that equation, and we see that we can divide out a sine of ct. And it'll go away from both sides, and we just end up with c squared equals k over m. Negative c squared equals negative k over m, but let's divide by a negative sine of ct, and the negative will go away as well. And it's very clear then that the solution is c is the square root of k over m. Now, I said use omega instead of c. And that's omega, omega, not w. People are going to want to write this as w. Don't do it. I warned you in class. That's a dangerous thing to do. Okay? Omega is the square root of k over m. And that's an angular frequency. We can go to the circular model of the trigonometric, the sine and the cosine functions, and see exactly what that means. We're not going to do that right now. I'm just going to say that this results in oscillatory motion. Okay, it results in an x value that starts at 0, goes positive, comes back to 0, goes negative, and comes back to 0, completing a full cycle out to distance a on one side and distance a on the other side. Full cycle completed as omega t changes by 2 pi, so that t changes by 2 pi over omega, so that the period of this motion is 2 pi over omega. Knowing the force constant and the mass, we can figure out then the period of the motion that's going to occur. Now that comes much later in the course, but you can understand why that would be a very handy thing to know. This also applies to circuitry, the oscillation of the Lrc circuit, and of course the model that you use to understand this function is the circular model. Running out of time, 15-minute limit in this video, but the circular model refers to a circle of radius a and a point moving around the circle at omega radians per second. the projection of this point onto a vertical axis gives you the simple harmonic motion of an object.